Okay, so welcome to section 9.8, which is Cramer's rule. Okay, so let's recall that for a matrix A, a 2 by 2 matrix A equals to AB, CD. We have that the determinant of A was the real number found by taking the product of the main diagonal and subtracting the product of the alternate diagonal, right? So this leads us to Cramer's rule. Okay, so let's let AX plus BY equal to H and CX plus DY equal to K. And let's have that the determinant of A, which is a matrix of coefficients, is not equal to 0. Then we have the following. X can be written as capital D sub X divided by the determinant of A, and Y can be written as capital D sub Y divided by the determinant of A, where capital D sub X is going to be the determinant of the matrix HK, then BD, and capital D sub Y is going to be the determinant of the matrix AC, and then HK. So notice I'm putting the constants in the column corresponding. So namely, this is X column, this is the Y column that is replaced with the constant coefficients. So for example, let's use Cramer's rule to solve the following systems. So use Cramer's rule to solve the following systems. Okay, so number one, let's say we have 2x minus 3y is equal to negative 1, and 4x plus y is equal to 5. So I claim that A, the matrix of coefficients, is going to be 2, 4, negative 3, and 1, which means that the determinant of A will be, the main diagonal is 2 times 1, minus the alternate diagonal is a negative 3, so this becomes 3 times 4. So that's going to be 14. Okay, well, I claim that capital D sub X is going to be the determinant of the matrix that swaps out the X column for the answers, negative 1 and 5, but keeps the Y column the same, negative 3 and 1. So it's just A, but the X column has been swapped out for the constants. Okay, so what is this? This will be negative 1 times 1 minus a negative, so plus 3 times 5. So capital D sub X is going to be 14. Okay, so capital D sub Y, I'll use this, capital D sub Y is going to be Well, the x column remains the same, 2 and 4, but now the y column is replaced with the answers -1 and 5. I take the determinant of that. So I get that this is 2 times 5 minus a -1, so +1 times 4. So 10 and 4 is 14. Okay, so I claim that x, which is capital D sub x, divided by the determinant of a, is going to be 14 divided by 14, which is 1. And I claim that y, which is going to be capital D sub y, divided by the determinant of a, is going to be 14 divided by 14, which is also 1. So these two together imply that the point in the plane where these two guys meet is 1, 1. So these two lines meet at the point 1, 1. Okay. So number 2, let's say we have the system x plus y is equal to 22 and x minus y is equal to 4. So I claim that the determinant of the matrix of coefficients is going to be the determinant of 1, 1, 1, -1, which is going to be -1 minus 1, or -2. I claim that capital D sub x is going to be the determinant of, I'm going to need more room, let me put this down one line. It's going to be the determinant that swaps out the x column for the answers, 22 and 4, and keeps the y column the same, 1 and -1. So that's going to give us a -22 minus 4, or a -26. And I claim that capital D sub y is going to now keep the x column the same, 1 and 1, and change out the y column for 22 and 4, the constant coefficients. So it's a determinant. It has straight up and down lines. Remember, straight up and down lines versus bracketed lines. So this is going to be 4 minus 22, which is -18. Okay, so these two together imply that x is -26 divided by -2, which is 13, and y is -18 divided by -2, which is 9. So the point in the plane where these two meet is 13, 9. Okay, so let's do one more. For third time's a charm. 1, 2, 3. Let's do 3x plus 5y is equal to 24. And -2x minus 3y is equal to -21. Okay, so the determinant of the matrix of coefficients is going to be the determinant of 3, -2, 5, and -3. So that's going to be -9 minus a -10. So that's going to be 1. Okay, capital D sub x is going to change out the x column in that determinant for the answers, which were 24 and -21. And keep the y's still 5 and -3. So what that's going to be, 24 times 3. Well, 20 times 3 is 60, and 4 times 3 is 12. So I claim that's -72 minus a -5 times 21. Well, 5 times 2 is 10, so that's 100, plus 5, so 105. Okay, what's 105 minus 72? Well, I claim if it were 75, the difference would be 30, but it's 3 more, so it's 33. So capital D sub, did I do that correctly? 24 times 3 is 60, and 12 is 72, plus 105. Yeah, okay. So 105 minus 72 is going to be 33. Yeah, okay, good. Just making sure. So D sub y will be the determinant. Now we're going to keep the x column 3 and negative 2. But the y column now will be swapped out with 24 and negative 21. Okay, so what do I get? Main diagonal. 3 times 20 is 60, so minus 63. Minus a negative. 2 times 24 is 48. So negative 63 plus 48. So the difference between 48 and 63 is 15, so that's minus 15. So I claim that these imply that x is going to be 33 divided by minus 9 plus 10 is, oh, yeah, did I get that right? Minus 9 plus 10, yeah, okay, is 1, right? Okay, just making sure. 1, so we get 33. Anything divided by 1 is just itself, so these are kind of silly, but that's okay. Minus 15 divided by 1, so I had to check that we were right. Okay, so minus 15. So the point in the plane where these two meet is at 33, comma, negative 15. Comma, negative 15. Okay, those are miserable numbers. Who came up with that? Guess we could always check it. 99 minus 50 is 49. Minus 25 is 24. Yeah, okay, it seems to work. Okay, so let's go on to the theorem. Next, theorem. So what about a 3 by 3? So all of this is for a 2 by 2. So how do I extend this to a 3 by 3? Well, first I need to find out how to take the determinant of a 3 by 3 matrix. So let's let A be a 3 by 3 matrix as follows. Let's have it be A, B, C, D, E, F, H, J, K, just because I is such a weird letter. We'll leave it off of here. Oh, come on. There we go. Okay, so then the determinant of A can be found as follows. Be found as follows. So the determinant of A is going to be the determinant of the following. We're going to have A, B, C, D, E, F, H, J, K, but then we're going to augment. And on the right of the augment, we're going to repeat the first two rows. So we're going to have A, B, D, E, H, J. Not the third row, just the first two, columns. What am I saying? Rows, columns. Sorry. And then we're going to calculate it as follows. It's going to be, so I'm going to color code this. We're going to have this first diagonal, this second diagonal, and this third diagonal. The products of those guys separately, and then we're going to add them up. So namely, we're going to have AEK plus BFH plus CDJ. And then we're going to subtract from that the following product. Let's do this maybe in orange. The alternate diagonal products and sums. So we're going to subtract from that now. CEH plus AFJ plus BDK. Okay, so that's how we're going to find the determinant of a 3 by 3 matrix. The product of all the main diagonals summed together minus the product of all the alternate diagonals summed together. Okay, so let's go ahead and do examples. So for example, so find the determinant of the following. Matrices. Okay, so number 1, let's say we have that A is equal to the 3 by 3 matrix. Let's do 1, 0, 0, then 4, 2, 0, and then 6, 5, 3. Okay, so I claim that the determinant of A is going to be the determinant of the matrix that takes the full matrix 1, 0, 0, 4, 2, 0, 6, 5, 3, and augments that with the first 2 columns, namely 1, 0, 0, and 4, 2, 0. So now what we're going to do is we're going to take the product of all the main diagonal entries so this is going to be 1 times 2 times 3 is 6, plus 0 plus 0 for the main diagonal entries. We're going to subtract from that the product of the alternate diagonal entries. What happened? Just tried to move it and it disappeared. Okay, so what do we get then? We get 0 plus 0 plus 0. Okay, thank God, that's nice. Very nice. So I can do this. This now becomes 6, right? Okay, that was easy. Let's do another one. Number 2. Where are my subscripts? So let's say we have that A is equal to the 3 by 3 matrix. I feel like I've got ants crawling all over me because I probably do. Okay, let's do -6, 1, 0, 4, 3, 0, and 3, 2, 5. Okay, so the determinant of matrix A is going to be the determinant we're going to do -6, 1, 0, 4, 3, 0, 3, 2, 5. We're going to augment this with the first two columns, which are -6, 1, 0, and 4, 3, 0. So now, let's go ahead and take the sum of all the, let's do this in darker colors. Let's try it in green. So let's do first, second, and third main diagonal entries. So I claim that that's going to be 30, -30 times 3, so -90 plus 0 plus 0 for the first three products, from which I'm subtracting. The alternate diagonal products and sums, which are going to be 0 plus 0 plus 20. So we get -90 minus 20 is minus 110. That's what I get for that. Okay, so number 3. Let's say that matrix A is, let's do 1, 3, 5, 2, 4, 6, 3, 2, 1. Okay, so the determinant of matrix A is going to be the determinant of, fill in the whole matrix, 1, 3, 5, 2, 4, 6, 3, 2, 1, augment. Put the first two columns, 1, 3, 5, 2, 4, 6. Okay, so now we're going to take the products, the sum of the products of all the main diagonal entries. 1, 2, 3. Okay, so what do we get then? We get 4 plus 20 plus 54, from which we're subtracting the product of all the alternate diagonal entries. Okay, so that gives us 60 plus 12 plus 6. Hopefully I did that okay. So that's going to be 78 minus 78. So all of that for nothing, or 0. Okay, so the determinant is 0. Okay, so let's note something about Cramer's rule. So note. So Cramer's rule can be extended to a 3 by 3. So Cramer's rule can be extended to systems in R3 where Z is simply capital D sub Z over the determinant of A. The same way, it's analogous. So for example, let's solve using Cramer's rule. The system let's do x minus 2y plus z is equal to 0. Let's do 2x minus y plus z is equal to 3. And let's do x plus y minus 2z is equal to negative 3. Okay, so first let's find the determinant of the matrix of coefficients. So that's going to be 1, 2, 1, negative 2, negative 1, 1, and 1, 1, negative 2, which we're then going to augment and just rewrite the two columns, 1, 2, 1, negative 2, negative 1, 1. Okay, so looking at the first set of main diagonal products and their sum, we get 2 minus 2 plus 2, from which we're subtracting the alternate diagonal sums. So that's going to give us negative 1 plus 1 plus 8. So of course the 2's reduce here and the 1's reduce here. So 2 plus 8 is going to be 10. Okay, now let's find capital D sub x. Well, that's going to be the determinant that swaps out the column for x with the answers 0, 3, negative 3. And the rest will remain the same. So negative 2, negative 1, 1, 1, 1, negative 2, augment. Now that to the right will be 0, 3, and negative 3. Then negative 2, negative 1, and 1. So looking at the main diagonal entries, we get then 0 plus 6 plus 3, from which we're subtracting the product of the alternate diagonal entries. Which is going to be 3 plus 0 plus 12. So I claim we get 9 minus 15. So if I did this right, hopefully I did this right, 0, 3, negative 3. Making sure I did everything right. So that's going to be 0, 6, and 3 is 9. Then we have positive 3, 0, and positive 12. Okay, yeah, I think that works. So 9 minus 12. Sorry. Here, why am I having so many issues? 3 minus 3 goes away. 6 minus 12 will be negative 6. So 2 minus 2 plus 2. Negative 1 plus 1 plus 8. Okay, just making sure. What color did I use for y? I forget what color I used for y, so I'm going to go ahead and use... I would like to use pink, but I've reserved that color. Shoot, I'm running out of colors here. I'll use hot pink for y, so capital D sub y will be the determinant of... So now the x column is going to be the same, 1, 2, 1. But it's a y column that's going to change out this time. So the y column is going to become 0, 3, negative 3. Hot pink. Then 1, 1, negative 2. Augment. I'll just use purple on the other side this time. Or actually blue. So 1, 2, 1. And 0, 3, negative 3. Okay, so let's look at the, oops, I should have kept the color the same. This is supposed to be hot pink. Okay, so now the product of the main diagonal entries. This will be negative 6, this will be 0, and this will be negative 6. So we get negative 6 plus 0, negative 6. Or minus 6, from which we are subtracting the product of the alternate diagonal entries, which are going to be 3 minus 3 and 0. So that's pretty easy. That's 3 minus 3 plus 0. So I can essentially ignore those guys because they sum to 0. As do these. Uh-oh. Look at this. Interesting. Is this going to be okay? Well, 0. Okay, so now let's do capital D sub x in, what color should I use? I like this bright green, but I've already used it. What color haven't I used? I haven't used orange. Let's use maybe a dark orange. So capital D sub z is going to be the determinant of the matrix that has x and y the same. So 1, 2, 1. Negative 2, negative 1, 1. But changes out now the z column for 0, 0, and negative 3. So let's do 0, 0, and negative 3. Then we're going to augment this with on the right, let's put in pink the first two columns. So 1, 2, 1, negative 2, negative 1, 1. Now go back to that. No, that's not the right color. This is the right color. So what do we get? So let's take the product of all the main diagonals and sum them up. So that gives us what? That's just 3 plus 0 plus 0. From which we're subtracting the product and sum of all the alternate diagonal entries, which are going to be 0 and 0 and 12. So 0 plus 0 plus 12. So we end up with 3 minus 12, which is negative 9. Okay, so now what is x? X is capital D sub x, which is negative 6, divided by a, the determinant of a, which is 10. So I claim that that's negative 3 over 5 when reduced. Y is going to be capital D sub y, which is 0, divided by 10, so we're okay. You can divide by 0. Sorry, you can have a numerator of 0. It's just that you cannot divide by 0, right? And z is going to be D sub z, which is negative 9, divided by 10. Okay, so these three together give us the point in 3 space that satisfies this equation, namely negative 3/5, 0, and negative 9/10. Ugly numbers, but at least I've shown we can expand to 3 space here. Okay. So anyways, let's go on to definitions. Definition. And this is going to have 2 parts. So part 1, an upper triangular matrix. Upper triangular matrix, that's the first definition. Denoted by U, capital U, for upper triangular. Has all entries beneath the main diagonal set to 0. And definition number 2 would be a lower triangular matrix. So a lower triangular matrix denoted by, you guessed it, a capital L. Oh, that's supposed to say has, not as. Has. So has all entries above the main diagonal set to 0. Okay, so that is i.e. id est, i.e. so an upper triangular matrix would look something like A, B, C, 0, D, E, 0, 0, F. So all entries above the main diagonal all entries beneath it are 0, right? And a lower triangular L, would be defined analogously, meaning it would look something like so. A, 0, 0, B, C, 0, D, E, F, where all entries above the main diagonal are set to 0. Okay. And you'll see that in linear algebra if you get that 4. Okay, so let's consider these then. So consider let's do the determinant of U as defined above there. Well, I claim that that's going to be the determinant of A, 0, 0, B, D, 0, C, E, F. We're going to augment that with the first 2 columns, A, 0, 0, B, D, 0. That's it. And that's going to be, well, first main diagonal here is going to be ADF and 0 and 0. So it's just ADF plus 0 plus 0 minus the alternate diagonal entries are going to be 0, 0, and 0. Okay, so this is just 0. So it's just ADF. ADF. Okay, now let's look at the determinant of a lower triangular matrix. So the lower triangular matrix in dark blue was A, B, D, 0, C, E, 0, 0, F. So repeating the first two columns, we get A, B, D, and 0, C, E. Okay, so what this gives us then will be, if I look at the main diagonals, ACF, 0s and 0, ACF plus 0 plus 0, from which I'm subtracting 0 plus 0 plus 0, which is just 0. So I end up with simply ACF. Okay. Well, what's interesting about that, those are the main diagonal entries, right? So note. The determinant of, wow, that's terrible. The determinant of an upper triangular matrix is the product, capital P, as my index counts from the first to the nth of E sub index index. So that is, i.e., the determinant of an upper triangular matrix is entry 1, 1 times entry 2, 2 times ... times entry n, n. It's all the diagonal entries multiplied together. And the same holds true for a lower diagonal. So the determinant of a lower triangular matrix will be the product, capital Pi, as my index counts from 1 to n, of entry, index, index, meaning row, column are the same. So that is the determinant of a lower triangular matrix is going to be entry 1, 1, entry 2, 2, ... times entry n, n, all of the diagonal entries multiplied together. Okay, so let's list the properties. Properties of the determinant. Properties of the determinant. Okay, so number 1, the determinant of an upper triangular matrix is equal to the product, as my index counts from 1 to n, of E sub index index. That is the product of all the diagonal entries. Similarly, the determinant of a lower triangular matrix is defined the same. It is the product, capital pi, as my index counts from the first to the nth of entry I. Okay. So number 2, the second property, is that if I swap row I with row j, this implies that the determinant of my matrix becomes negative. So actually, let me annotate that with. That has to do with swapping. So let me actually write this like so. So when we swap any two rows, we change the sign of the determinant. Okay, so property number 3. If I have that row I is equal to row j, then this implies that the determinant of my matrix A is 0. So if any two rows are the same, the determinant is 0. Okay, so number 4. If row I is equal to 0, or, actually let me do the or in a different, or column j is equal to 0, if either of these cases are true, then the determinant of A is 0. Okay, the next property, number 5. The determinant of the inverse of a matrix A inverse, is just 1 over the determinant of matrix A. It's literally that easy. Okay. Number 6. So we are on number 6. If I have k times row I then this implies the determinant of this new object is going to be k times the determinant of A. Okay, so let's note something. So adding / subtracting one row from the next does not change the determinant. So we can perform some determinant elementary row operations without changing the determinant. So for example, let's find the determinant. Find the determinant of A using properties. And elementary row operations. Row operations. Then prove. Okay, so let's say we have that A is the 3 by 3 matrix given by, let's do 1, 3, 0, 2, 1, 4, and 4, 4, 0, 3. I feel like I'm gonna sneeze. Yep, I'm gonna sneeze. Okay, pardon me. Okay, come on. Okay, so let's go ahead and start with our elementary row operations like we would solving an augmented matrix. So 1, 3, 0, only we have no augment here. 2, 1, 4, 4, 0, 3. So my goal is to get an upper or lower triangular matrix. So let's go ahead and do row 2. Minus 3 times, let's do row 1. Just to make that a 0 in that spot like we would usually do. So this is going to be 1, 2, and 4. But now 3 minus 3. Oh shoot, I should put an arrow here. Put it in yellow. Okay, so 3 minus 1 times 3 is 0. 1 minus 3 times 2 is negative 5. 0 minus 3 times 4 is negative 12. Negative 12, and row 3 remains 0, 4, and 3. So what did I do? I just added the entries of one row to another. So do you agree this is no change? No change in the determinant of A. So I haven't changed the determinant by doing that. Okay, well, let's continue. Let's do row 2. Let's do plus row 3. And you'll see why I'm doing this in a moment. Row 3, I guess I'll do in green. Okay, so row 2 will be changing, row 3 will stay the same, and row 1 is the same. So 1, 2, 4. Now, row 2 plus row 3, 0 plus 0 is 0. Negative 5 plus 4 is negative 1. Negative 12 plus 3 is negative 9. And then 0, 4, 3. And remember, adding or subtracting rows doesn't change the determinant. So this is still no change. No change in the determinant. Okay. So now I'm going to do row 3 in green. So row 3. Let's do plus 4 times row 2, shall we? Let me move that down. So row 3 is going to change this time. Let me move this a bit to the left. Okay. So rows 1 and 2 will stay the same. So we'll have 1, 2, 4, then 0, negative 1, negative 9. So 0 plus 4 times 0 is 0. 4 plus 4 times negative 1 is 0. And 3 plus 4 times negative 9 is going to be negative 33. Okay, so this is also no change. No change in the determinant. But what's nice now, do you agree that what we have here, this is an upper triangular matrix, right? this is u. So I claim that this implies the determinant of u is going to be the determinant of a, but the determinant of u is what? It's going to be 1 times negative 1 times negative 33, which is the determinant of a. So let me actually write that formally. This will be our answer, so I guess I could put it down here. So, let me delete it. So, I'll write it this way. I'm trying to figure out what's a good way to write it. So the determinant of u, I claim, is the product, as my index counts from 1 to 3 of entry index. So that's going to be I want to be explicit here. That's going to be entry sub 1 1 times entry sub 2 2, second row, second column, times entry sub 3 3, third row, third column. Okay, so that's going to be entry sub 1 1 is 1, entry sub 2 2 is negative 1, and entry sub 3 3 is negative 33. So when all is said and done, we get positive 33. Well, let's check it. So I claim that that is the determinant of A. Well, I can check it using my augmented matrix thingy. Okay, so let's check. And of course, thingy is a technical term. Okay, so the determinant of A is going to be the determinant of, move this, I can't stand that. Okay, so what was A? A was 1 3 0, so 1 3 0, then 2 1 4, 2 1 4, then 4 0 3, then 4 0 3. I'm going to augment that and put the first two columns on the right. So 1 3 0, 2 1 4. So let's see what we get. If we take the product of all the main diagonal entries, let's do that in green. That will have 3 plus 0 plus, what's that, 12 times 4? It's 48. Okay, so we're going to have 3 plus 0 plus 48. We're going to subtract from that the sum of all the products of the alternate diagonal entries, which are 0, 0, and 0. Those are numbers I like. Okay, so 0 plus 0 plus 0. Did I do this? Am I doing something wrong? Why am I getting... I should not... Oh, yeah, okay, duh. I'm an idiot, because this last diagonal is not 0. That's why. Okay, notice there's a... Oop. There is... This diagonal is not 0. I don't know what I was thinking. 3 times 3 is 9 times 2 is 18. That'll be better. I was going to say, what did I do wrong? I skipped. So what do we get? We get... So 3 plus 48 is going to be 51 minus 18. Okay, so if I subtracted 20 from 51, I would get 31, but I'm too shy, so that's 33. Holy free holy, we did it. Thank goodness. Check mark. It does work. Okay, so I think I will let you here, and that is the end of chapter 9.